So I'm going to be talking today about two-source interference of waves. Assume that you have two traveling waves. In this case, they're represented by oscillations about a mean position, and these waves could either be traveling to the right or to the left, and we're going to assume that both of them are traveling either to the right or to the left. So these waves they could be in sync like this one, or they could be out of sync. By out of sync, I mean they could be off by half a wavelength. So if you notice, this distance is precisely lambda by 2. Of course, half a wavelength is the minimum amount by which it could be off. It could also be off by 3 halves or 5 halves, 7 halves, and so on. Whereas these are in sync, which means they are either 0 lambda apart or maybe an entire lambda or 2 lambda apart. So what happens when you add these waves? If I were to add them, then I'll get a wave that will reinforce itself at these crests and at the troughs. So if I were to try to draw this to scale, it would look like this. So I made sure that I have 1 unit here and 2 units now on this one. Like so. So the peaks will be reinforced, as will the troughs. This particular mode of adding is called constructive interference, or more precisely, it's the fully constructive interference case. What about here? If I add the crest to the trough, I get nothing. Similarly, the trough to the crest, I get nothing. So I end up getting a flat line. So that would be the case of the fully destructive interference. If you have a noise cancelling headphones, then what it does is the moment the noise cancelling headphones gets a signal, it adds lambda over 2 to that signal and sends it back to your ear along with the original signal, so your ear will now detect nothing, and that's how noise is cancelled by noise cancellation headphones. Now these limits, fully constructive and fully destructive, are two ends of a spectrum. There's going to be all gradations between the fully destructive case and the fully constructive case, and that I will not be doing in this course. You will more properly study all the in-between gray areas in UP2 when they study interference in the context of multiple slits and light going through multiple slits. So I just want to emphasize here that if your waves are off by multiples of lambda by 2, then you get fully destructive, and if they are off by multiples of lambda, then you get fully constructive. Let me summarize that. The path difference will be multiples of lambda, m lambda, where m equals 1, 2, and so on. And here the path difference between the two waves will be m plus a half lambda. Now this way of writing will take into account that m equals 0. That's also allowed here, by the way. You can be off by 0. 1, 2, and so on. So for example, if I put m equals 0, I get half lambda, which will be this case. If I put m equals 1, I'll get 3 halves lambda, which will be the whole thing shifted by 3 halves. It'll still look like that. So that's the more general expression for the path difference. Let's try to apply this to a real-life problem. One of the real-life problems that you may have in setting up your home audio system will be to locate where any dead spots may occur in your music listening experience. So here's a concrete example. Let's assume that you have two loudspeakers, and for the purposes of this analysis, I'm going to assume that the loudspeakers are not playing any complicated music, but just pure tones. So you feed them both with a amplifier with no phase delay. So the amplifier feeds the same signal in the form of a frequency to those two speakers, which are identical in all respects. And then these two speakers will emit a sound which you will then hear depending on your location. Now everybody knows that the sweet spot is going to be somewhere here because the waves are going to come with no path difference, and so you'll get the best effect if you sit in a position where the line joining the speaker and you and the speaker and you and the speaker and that speaker form an isosceles triangle. Some people swear by equilateral, but I think isosceles works just as well. Let's try a more interesting problem. What if your seating arrangement calls for you to sit here? So let's call that the point P. And now you're beginning to wonder, geez, now I've trapped myself in that corner. So I want to make sure that I'm able to hear at least the frequencies that you enjoy. Let's suppose you enjoy some instrument like the cello. So one of the primary frequencies of the cellos you want to be able to hear. So you have in mind your favorite lambdas for which you would like a constructive or a very strong sound there. So let's assume you have something like that. Let's call this distance x because x is the variable distance. And the distance between the two speakers, let's assume that you have very little control on that depending on the size of your room and the specs of the speaker manufacturer, who may say that you have to keep the speakers a certain distance apart and a certain distance away from the walls. So one is usually constrained by those requirements to keep d more or less fixed. So now, by the Pythagorean theorem, this distance is going to be square root of d squared plus x squared, since this is a right angle triangle. And so we can actually have a concrete formula for the path difference. The path difference in this case is going to be the square root of d squared plus x squared minus x. I put the longer distance first because I wanted a positive quantity, since I've always assumed that this is positive. So let's find out the worst place to sit. The worst place to sit would be m plus a half lambda. So that will tell you where not to put your couch. So let's write that. M plus a half lambda equals the square root of d squared plus x squared minus x. Now if you want to solve for x, the best bet is to bring the x over to this side. Otherwise, each time you take the square, you keep getting the square root back, and that will not be a good thing. So bring the x to this side first, and then go about squaring both sides. Now if you square both sides, here I'm going to get m plus a half squared lambda squared. That's a plus b squared, so that's a squared plus 2ab. So that's 2 times m plus a half lambda x plus b squared. And here I just get rid of the square root sign. You observe that the x squareds simply cancel out. So I have actually a very linear equation for the position that you should not put your couch at. So this is going to be x equals, now I'm going to take this over to the other side. So it's d squared minus m plus a half squared lambda squared divided by everything that multiplies x. That is your master formula for the subject matter at hand, which is where not to put your couch. Now you notice that it certainly depends on the frequency, so you have to pick and choose what your favorite frequencies are, because depending on the frequencies, you can either have a good spot or a bad spot. What is a good spot for one frequency will be a bad spot for another frequency. That is why you have to kind of pick and choose here. Let us take some simple examples of certain frequencies that you may want to keep. So I'll see what happens when m equals 0, okay, in that formula, just to get some basic insight about speaker placements. So let's take m equals 0. That gives us the most basic positioning. So I get x equals d squared minus lambda squared over 4 divided by just lambda, because the 2 and the half cancel each other out when m equals 0. So that's a pretty simple formula to work with. Now you'll notice that, interestingly enough, there is one interesting value, x equals 0. Well, x equals 0 seems to make no physical sense because you're literally at the speaker, your ear is right against the speaker. But it's still worth examining what that really means. So let's put x equals 0. Well, nobody's going to sit that close, but anyway, let's see what that gives us. It gives us that lambda must be equal to 2d, because I get lambda squared equals 4d squared, which means lambda equals 2d. That's a pretty interesting result. So let's see what that really means. Okay. Now d for a typical loudspeaker is about 2 meters. So I'll just say 2 meters. It's about 6 feet apart. Most people keep their speakers around that, if not a little this way and that. So 6 feet or 2 meters apart. Let's see what that gives us for lambda. I get lambda equals 4 meters. We can actually find the frequency that this corresponds to based on sound, because these are loudspeakers. You've got to use the speed of sound here. The wave relation for sound is the speed of sound equals lambda times the frequency. So the speed of sound in air is about 343 meters per second, and that's equal to lambda, which is 4 meters, times the frequency f. So solving, I'm going to get f equals 343 over 4 hertz, which is around something like 75 to 80 hertz. I'll just say 80 hertz approximately. So that's an interesting result in itself. It means that whether or not you're listening, there is going to be an 80 hertz dip in your frequency response intrinsic to the speaker itself. So your speaker designer, anticipating this, may usually design the speaker to give a little bit of a boost at the 80 hertz range, because the room acoustics itself, the intrinsic room acoustics, is going to suck it out at 80 hertz. So that's called the intrinsic suck out, based on just the speaker placement. So that I thought I'd mention that to you. This name is actually a pretty technical name. You can find it in all kinds of loudspeaker reviews. So it's they would say the speaker's got to suck out at 80 hertz depending on the room placement. Other than that, you can just put whatever value of m you want here. And if you want to look at other different frequencies, for example, if you want to figure out where to put your couch to listen to the fundamental frequency of a cello, let's say you want 100 hertz to be really prominently featured, then you would take the frequency corresponding, the wavelength corresponding to 100 hertz, put it in this formula, and then find the x and stay away from that x. Another way you can do this problem is, rather than figure out what x is to avoid, you can rather choose to put m lambda instead of m plus half lambda, and that will tell you where to actually put the speaker. You can also do that. I went this route, but you could as well have put path difference equals m lambda and solve the whole thing with just m lambda here. The only difference is this would be x equals d squared minus m squared lambda squared divided by, here you get 2m lambda. And that would give you the positionings where you need to sit to listen to a specific frequency instead of where you do not need to sit. But I'd rather find where you do not need to sit so that you can avoid that. And if you either put it a little bit before that or a little bit after that, you're safe. So it's always better to find out where not to sit. And there you have some freedom to put your couch in either a little bit forward or a little bit backward from there. So anyway, I thought this would be a neat application of something that people think about on a daily basis. Now, real music is very complicated. It's made up of a number of frequencies. So this one frequency deal calculation doesn't really matter. Also, don't try to calculate like this when you want to find the proper seat in an orchestra, when you want to go to a concert in Eastman Kodak or something. You don't have to make this calculation beforehand, because there are many things that I've not even considered, such as reflection of sound waves. Most of the sound waves that you're hearing in a concert hall are reflected sound waves from various walls and various other people in the concert hall. So there's no such thing as a real sweet spot. Some people swear by sitting right in the middle of the entire orchestra pit over there, they try to pick this seat and pay. And sure enough, the Eastman Kodak's box office tends to charge a lot of money for those special sweet spot seats. But you can really sit anywhere you want, and since music is made up of a lot of frequencies and wavelengths, you won't really miss out, and there won't be any suckouts. It's not like you can suddenly not hear the trombone or the double bass or something like that.